Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue thinking about streams and flooding. So in this video we're going to think about what is a flood and what is not a flood, and this is going to correspond to section 16.12 of the textbook. So typically, if for something to be considered a flood, water needs to exit the river channel and cover the surrounding area. This isn't a huge surprise to any of us because that's what we think of when a flood occurs. Now, if water is not exiting the river channel, we obviously don't have a flood event going on. Now, there may be times when the discharge of the river increases, so we have more water passing through our river channel faster, and this can lead to periods of erosion where the banks especially begin to be degraded by this increased discharge. However, the water in the river doesn't actually exit the main channel. So in these events where we have increased discharge and therefore increased erosion of the banks, people will often refer to these events as floods, but in a strict sense they are not actually flood events. We need the water to be leaving the channel itself in order for us to actually have a proper flood. Now, once the flood overflows the channel, it will spill onto the surrounding floodplain. And we know by now that when the water exits our river channel, it's going to start decelerating relatively quickly. So it's going to start slowing down. And this means that the sediment which is brought out with the water from the river channel is therefore going to be deposited over the area which gets flooded. Now, within the channel itself, well, should I say along the margins of the channel, we can have the formation of levees, and levees are actually helpful because a levee is of course an area of raised terrain either side of our river channel, and the presence of levees actually helps to reduce the chance of flooding because the levees essentially are going to act as an additional barrier to stop water exiting our river channel and heading out across our floodplain. So some levees can be natural in their formation, but humans have also decided to produce artificial levees, so we'll build up soil and loose material along the edge of rivers, or we can actually install concrete barriers which act as artificial levees, and that actually increases the total volume of our river channel. So during an event where we have high rainfall, the discharge of our river may increase, but because we've added this extra volume, it means that the river will not be able to flood out of its channel over the surrounding area. The final thing that's going to occur is, of course, as I've said, as the water exits the channel and spreads out across the floodplain, it's going to decelerate. And this is going to lead to sediment being deposited as the water begins to slow down. Now, we've already discussed in an earlier lecture how we're going to have the coarsest sediment being deposited closest to our river, and steadily as we move away, we are going to get steadily finer sediment. So when we look at our floodplain here's our river channel. We know we're obviously going to have a sandier material being deposited here along the margin of our river channel, and then as we move out onto the floodplain proper, we know that the water is going to be depositing more silt and clay-rich material. So when we're talking about floods, it's always useful to display what's going on in the form of a hydrograph. So once again, like all hydrographs, we have time on this axis and discharge on this axis. So if you remember, discharge is simply the area of the river multiplied by its velocity. So we'll find a point on our river, we'll work out the area for that portion of our river channel, and we'll work out how fast the water is moving. We'll take that measurement, and from that we can calculate our discharge. Now, the blue line here represents the discharge of our river, and the red line represents what's referred to as the flood stage. And the flood stage represents the level of discharge at which water will start leaving the channel. So that's the point where our flood is actually going to begin. So in this instance, you will see the discharge of our river falls well below the flood stage, and so we are going to have no flooding occurring. And this is obviously the situation which we want. So, as we've discussed, one of the things that we can do in order to try and stop flooding is to increase the size of the levees. And by adding the extra volume, what that does is it means the discharge has to get even higher before a flood can occur. And so by building up levees, we actually end up pushing the flood stage higher. So we make it more difficult for our river discharge to ever exceed the flood stage. Now, when we have floods, we tend to see they occur in one of two forms. The first thing you'll notice in both of these diagrams, you can see the discharge of our river, marked out by its blue line, has exceeded the flood stage. So as soon as our discharge meets and starts to go over the top of the flood stage marker, we have water exiting the channel and spreading out over the surrounding floodplain. Now, you'll notice that the increase in discharge can either be slow or quick. And this depends on the type of process which is moving water into our river system. So in this case, we can imagine a situation, let's say, where we have snow melting at the start of spring. So what we have steadily over time is we have the temperature beginning to increase, the snow starts to melt. Initially only a small amount of the snow will melt, but the temperature keeps getting higher, so more snow melts. And then the temperature keeps getting higher still, and even more snow melts, liberating more water which starts going into the river network. And so what's going to happen is over time we're going to see the discharge of our river increasing as more and more of that snow is melting, adding water into our drainage network. And eventually the discharge begins to exceed the flood stage. So we have a flood event going on. The discharge keeps going up as more and more snow is now melting, liberating more and more water, which is going into our river network. And eventually we reach the peak discharge right here. And then steadily the discharge begins to drop because the amount of snow melting begins to decrease because most of the snow has melted away. And so this is a pretty standard flood diagram to have where we have a long drawn out event. So it could be something like snow melting, or it could be something like a prolonged period of rain. So several days of rain slowly saturates the ground, and steadily over time that rainwater begins to move into our drainage network, and we see the discharge steadily creeping up. We see the discharge exceed the flood stage, reach the peak discharge, and then steadily go down on the other side as the storms begin to subside. Now, in contrast, over here on the right, we have a rapid flood, and these are going to often be produced by relatively short-lived events. So we're going to think of events like very short-lived, very strong thunderstorms, or maybe some kind of event like a dam failure, releasing large amounts of water into our river network. And so obviously what you can see is in this portion here, we can see our discharge is well below the flood stage, so our river is perfectly fine. And then all of a sudden right here, you will see there is a very rapid increase in river discharge. And this is because a large amount of water has been added to our river in one go. And so we can see the discharge shoots up very, very quickly, reaches the peak discharge, and then, once this additional water has moved through the system, we see the discharge dropping down quickly on the other side as well. And so these rapid floods will often produce peak discharges which are very, very high, but the flood event itself will often be relatively short-lived. And so, as I said, this is the kind of situation we expect to get where we have a large amount of water being added to our drainage basin very, very quickly. So a large summer thunderstorm would be a great example of this kind of process. So what are some of the causes of flooding? So what I've tried to do is I've tried to split some of the common causes into two groups. There are natural causes and there are man-made causes, because, in some instances we are more to blame in terms of causing flooding than nature. So in terms of natural sources of flooding, one of the most common ways this can occur is snow melting. And this will obviously occur in higher latitude areas in the southern and northern hemispheres. So these are areas which will often have relatively cold falls and relatively cold winters. You'll get an accumulation of snow and ice, and this will begin to melt in the spring, and this, the water will steadily be added to the drainage network, and eventually, if sufficient water is added, it will exceed the flood stage. Now, in terms of precipitation can occur in two forms. You can have localized heavy precipitation, so that would be something like a thunderstorm. It affects a relatively small area, and so typically the flooding will often be limited to the drainage network below that area. You can also have regional precipitation in the form of hurricanes and typhoons, and so this is where you're going to have a large amount of water being deposited over quite a large area. And so this is going to cause multiple rivers within that area to begin to increase their discharge and possibly flood simultaneously. So this can actually lead to extremely damaging, extremely large-scale flood events. Now, another event which can cause large-scale flooding is the failure of ice dams. So it's not uncommon in areas where you have a large build-up of ice and snow for this snow to begin to melt as the climate warms up. Now, very often this water will be able to escape freely and it will enter the drainage basin and eventually work its way to the ocean. But in some cases, the water will actually get trapped behind a barrier. And in some instances, these barriers can be made of ice. So a classic example of this would be a melting glacier. It's not uncommon when a glacier melts for there to be, a piece of ice that blocks the escape of the water. And so behind this ice dam, we have a build-up of liquid. And eventually the ice dam will fail. Either the ice dam will melt and become weaker, or the weight of the water behind the ice dam will become so great that the ice dam will fail. Either way, that water that was trapped is suddenly released and it comes shooting down our river system. Now, another thing that can lead to flooding are volcanic eruptions. More accurately, volcanic eruptions which are associated with explosions. So we're talking about volcanic eruptions associated with composite volcanoes and volcanic domes. Now, the reason for this is during the explosive portion of the eruption, we know that a large amount of ash and dust gets thrown up into the atmosphere. Now, these small particles, as they enter the atmosphere, will act as nucleation points for little droplets of water that are suspended in the air. So these little droplets of water will start to gather on the surface of these ash and dust particles, and eventually the buildup of water will become so great that the resulting particle of water will be too heavy to be suspended in the air, and so the particle, or the blob of water, will have to fall from the air in the form of a raindrop. So imagine where you have a volcanic eruption putting large amounts of ash and dust into the atmosphere. Well, that means you're going to have multiple nucleation points. A lot of the moisture in the air is going to start nucleating on these ash and dust particles. And so what can happen is large volcanic eruptions are very often followed by large thunderstorm events. And so what will happen is after the volcanic eruption, it's not uncommon for these big thunderstorms to occur. Large amounts of water will be deposited across the area close to the volcano relatively quickly. This can obviously lead to floods, but it can also lead to other dangerous events such as mud flows, when you have a mixture of this rainwater plus the poorly consolidated ash and dust all mixing together to form a mud flow that will also come shooting down the side of the volcano and unfortunately possibly hit settlements. The final natural cause of flooding can be dam failure. Now, dam failure can also be man-made because, of course, we have man-made dams and we have natural dams. In the case of a natural dam, this could be something like a beaver dam. So if you've ever been and seen a beaver dam, you'll know that they can actually be very substantial bodies, and they can actually cause a large amount of water to build up behind them. Now, obviously, bearing in mind they're made of organic material which will rot over time, beaver dams can fail. And so if the dam isn't being kept up by the beavers, it will eventually fail, and this will allow the water that was trapped behind the dam to flow downstream. Now, we can also have man-made dams. These too can fail, and this will lead to the same event. The water that was built up behind the dam will then be allowed to flow downstream, causing a flood event, because we'll have a sudden large amount of water heading down our river. We're going to have a massive increase in discharge, and that will push the discharge above the flood stage. So, in terms of man-made causes of flooding, there's two main ones. The first one is urbanization. So in urbanization, what we're doing is we're taking areas which are essentially untouched by humanity, and we are building over the top of them. So we're taking the ground, we're compacting it, and we're laying down cement. We're laying down concrete, which is of course impermeable to rainwater. And so what will happen is when there's a large rainstorm and the rainwater hits the concrete, it flows across the concrete, and that means the water can enter the river more quickly. In contrast, if the area had been left natural, what would happen is the rainwater would hit the ground, it would start flowing across the ground, but the ground is covered in grass. That would help to slow down the flow of water. Some of that water would sink into the soil, once again helping to slow down the entrance of that water into our drainage basin, into our drainage network, should I say. And so by replacing natural conditions with cement and concrete, essentially what we end up doing is we end up making it easier for the rainwater to enter the river faster. And so because we're managing to channel this water into our river at an increased speed, this increases the chance of there being a discharge which will exceed the flood stage. On top of that, what also tends to happen is human beings want to get the water out of their area as fast as possible. So obviously we'll build a drainage network into our urban areas to transport this wastewater away. And where does this wastewater tend to get channeled? The answer is, of course, straight into river channels. And so we're not only, making it easier for the water to flow across the surface of the earth by putting down all of this concrete, what we're also doing is we're actually helping to channel the water which we collect into the river as well. So you can see we are, making the situation doubly worse. Now, another factor which can affect flooding is deforestation. So in the case of deforestation, we're cutting down trees. So you're instantly thinking to yourself, well, hold on a second, how are trees going to help with flooding? Well, think about a situation where we have a rainstorm going on. So we have a drop of rain, it falls from the sky and it lands on a tree. So it hits the top leaf of the tree. Well, that drop of rain then rolls down and hits another leaf. That rolls off, hits another leaf, hits another leaf, hits another leaf. On the way through the tree, this raindrop may pass between 50 or 100 leaves. So that means it's taking more time to make it from the top of the tree to the ground than it would if the tree wasn't there. So if there's no tree, the raindrop simply comes straight from the sky and lands straight on the ground. Now, if you have an area which is quite heavily forested, what this will mean is the presence of all those trees will impede the rate at which the rainwater can make it from the sky to the ground, because a lot of that rainwater will get caught up moving through the trees, and so it helps to slow down the process. And so this means you're not going to get a glut of water heading into your river all at the same time. Instead, it means that the water is going to be spread out over a longer time period, and this is going to reduce the chance that the discharge of your river will exceed the flood stage. All right, thank you for listening, everybody, and have a good day.